Okay, so here's a problem. Let's look at it quickly and see what we know. So looks like A is going to be a roller. B is a hinge, and then C is a fixed connection. So we've got to do some work before we can even get started to know what the shear and moment at A, what those values are, what the shear and moment at B, and what the shear and moment at C. So it's not a difficult problem, but it's not trivial to find all those reactions. You can probably notice if you tried to draw a free body diagram for the whole structure, you're not going to be able to solve for it because you're going to have 3 unknowns at the fixed connection, an additional unknown at the pin. That's 4 unknowns, only 3 equations. You won't be able to get it. So you're going to have to take it apart here at B. And at B, you would only generate 2 unknowns, but you would get 3 more equations. So that'll make it determinate. So I'm going to draw it over here that way. I'm going to go ahead and separate it at B and draw a free body diagram from A to B, and then another one from B to C. So I'll start at the top, say free body diagram from A to B. So I will draw that. There she is, 6 feet tall, 6 feet long. I will assume at A, I will draw at A positive shear force. And at B, I will draw positive shear force. There is no moment at A. There is no moment at B. On top of that, I will replace this distributed load with a concentrated equivalent force, which will have what value? Well, the area of the curve. So the area of a triangle is 1/2 base times height. Looks like 450 pounds. And that'll be about right here. And I know the centroid of that is 1/3 the distance from the bigger end. That's 1/3 of 6 is 2 feet. And it would then be 4 feet from the other end. Now, before I even move on, if you look at this problem, I can solve this side. I only have how many unknowns? 2. And I can write the 2 equations very quickly. I can sum moments about some point. I can sum forces in the y direction. So I'm just going to go ahead and solve what I need right here before I go any farther. So I will sum moments about A, just because it comes first in the alphabet, no particular reason. And then summing the moments about A, my concentrated equivalent force creates what kind of moment? Negative. So it'll be the force, which is 450 pounds, and the moment arm is 2 feet. And then the shear at B also creates negative moment and has a moment arm of 6. So I should be able to solve for the shear at B, and I think it comes out negative. And I don't know what it's going to be. 150 pounds? I guess I do know what it's going to be. So that means the shear at B is positive or negative? Negative. I can find the shear at A now. All I have to do is sum all my forces in the vertical direction and make sure they're in equilibrium. So I'm going to assume up is positive, so the shear at A is up. The shear at B is down. My concentrated equivalent force is down. If I put my negative 150 in for the shear at B, what do I get? Positive. So that means the shear at A is positive. And it's equal to 300? Wow. That kind of worked out. Is that a surprising result? No, usually in a kind of a simple supported beam, which is what this looks like, with a triangular load, usually 1/3 of the total goes towards the big end. 2/3 of the total goes towards the big end, and 1/3 goes towards the little end, and that's exactly what we got. So I feel pretty good that that's right. So now what do we do? There you go, free body diagram for BC. So I'll draw that. 3 feet long. Now, I've already assumed positive shear force here, so I'm going to put positive shear force here. I'm going to come to C, and I'm going to assume positive shear force. And positive bending moment. Now, in this little segment, I have this triangular shape. So to find the concentrated equivalent force of that, I'll take that area. 1/2 base, 3 times height, 150. Is that 225? And the centroid will be 1/3 the distance from the big end. 1/3 of 3 is 1 foot, and this side will be 2 feet. Now, I already know the shear at B. What is the shear at B? Negative 150. So when I write my equations to solve for the stuff at C, I'm just going to use this value. But when I compute it, what am I going to plug in? Negative 150. So I'll start by summing the moments at C. Make sure the thing is in equilibrium. So starting at C, what kind of moment is this with my sign convention, right-hand rule? It is positive. About C, what kind of moment does the 225-pound force create? Positive. So the force is 225, and the moment arm is 1 foot. And then the shear at B, the way I've drawn it, what kind of moment does it create? Negative. And has a moment arm of 3. So I'm going to solve for the moment at C. So I'll take my negative 150 and put it in there. That becomes positive 450. And when I add it to the positive 225, I get, what is that, 675? And that's all positive, so that goes to the other side of the equation. It becomes negative 675. What else do I need? Shear at C. I'm kind of running out of space down here. Can I stick it over here in this corner? Is that okay? So I'll come back and sum forces in the y direction. What do I have? Well, I've got my shear force B is up. My shear force C is down. My load is down. Remember, shear force at B is negative. Plug that in there. So what is my shear at C equal to? 375? No? Bueller? Is that too old a reference?
No, we get it.
You just don't like it. I get it. I get it. Didn't swag a curve on that one.
That's pounds.
What's that?
That's pounds.
What did I write? Oh, that would be a terrible value. Yeah, it's pounds.
Whoa.
I don't know what that is. That doesn't look like anything. It looks like a hieroglyph. LB. Why is LB the shortcut for pounds? Figure that one out. Why not P?
It's a British thing.
I don't know. Everything's a British thing, isn't it? We're Americans. Everything comes from Britain. All right, so let's make our template. So there's the left edge, and there's the right edge. My youngest son is learning to spell, and he's really fascinated by the silent E at the end of the word. And he basically says, what the hell is up with the silent E? Now, I've always thought, wouldn't it be nicer just to say A, and if you want to make a different sound, put a little notch on top of it. So one is A and one is A. Why do I have to look at the very end and see if there's an E to know if I say A? And he's trying to figure that out, and I understand. I said, I feel your pain. It's just the way it is, you know? And if you read the history of the English language, it's not like it came from one place. It's like every language in Europe. has been squeezed in and twisted and mangled and created English. And then the English came to America in the 1600s and just fouled the whole thing up from that point on. It's terrible language. Terrible. I don't know how people learn it, to be honest with you. I don't know how to speak it. Here's another spot that's important, B. Why? Something's going to happen there. Not only is our load changing, but we know something's going to happen. What's going to happen there? What's the moment going to be at B? Zero. So let's draw a template that indicates the positive direction and the positive value for shear. And what are our units? LB. Yeah. Lub. How many lubs do you weigh? All right, so what do we know about shear? What is the shear at A? 300 pounds. Positive or negative? Positive. Do we know the shear anywhere else? What is the shear at B? Negative 150. What is the shear at C? 375. So now we just have to fit it. I've run out of, I guess I can squeeze them in down here. So the change in shear is the area under the load curve. Oops, and the slope of the shear diagram is equal to the load. This is that's the way the Pilgrims wrote B. So what is the change in shear over the first 6 feet? Would be the area under the load curve on the first 6 feet, which is what? It's a triangle, 1/2 base, 6 times height, 150. That's 450. Is it positive or negative, the loading? Negative. So 300 minus 450 is? 150. Hey, that's good. I like that. The shape of the shear diagram, I know it doesn't look like a V, but that's what it is given by the load. What is the load? What does the load start off as? Negative and goes to? So here is a negative slope, and here is a 0 slope. And what are we going to do, Mr. Van Tilburg? I'm going to swag a curve. Now what? So what is the change in shear between B and C? Area of this curve. What is the area of that curve? 1/2 base times height, which is negative 225. So you subtract that from 150, you get success. Now the slope of the shear diagram is the load. What is the value of the load at B? 0. 0 slope. And it increases to a value that is negative. So it kind of has a little inflection and goes the other way. That's a pretty cool looking shear diagram. Something has happened though, and it doesn't look good. What has happened? We went across the axis. We need to know that value of that point, say x1. How are we going to do that? Okay, I'm going to show you a way, and you're not going to be happy about it. If I extend that up to the graphic method, it says that the change in shear between here and here, which is what? Negative 300, should be given by the area under the load curve. Ouch. That's going to be a little tricky to do. Now you can do it, obviously. You can say, well, I know this base is x1 when I'm trying to find, but what's the height right there? It's a function of x1. So that area is going to be a quadratic in x1. You'll get two roots. One will be reasonable, probably between 0 and 6, and one will be not reasonable, not between 0 and 6. No. So what do you do at this point?
Don't give these on the table.
I actually can. What would you do? You might want to rethink your approach. What would be a better approach, possibly?
Move forward and see
Huh?
what's in the future.
What's that? Look into the future?
Move on and go to the future.
Oh, we could write an equation.
You could write how many equations?
Maybe one. So that's 6.
2.
2 equations?
And then you would have an equation for shear that would give you this, which you could integrate and you could get your moment. So it's going to be really tough graphically to figure this out. You might be thinking to yourself, oh, is this a quadratic parabolic section? No, it's not. You'll see that at this end and at that end you've got varying slopes, but none of them is horizontal or vertical, so it's not a clean section of a parabola. So I don't know what that is. I'm kind of like, well, what do we do? I don't know what we should do. Maybe not have gone down this path to start. But we have, so now we're going to learn from our mistakes and not continue on this path again. When you see triangular loads, especially lots of them, you may not want to do that graphically. You may want to write some equations. But we can probably quantitatively figure out what the shape of the moment diagram would be, but not, qualitatively, but not quantitatively. I can get the shape, but I won't be able to tell you the value. Because I can assume that this is a positive change up, and then negative, negative, negative down. So I can get like a kind of a shape, but I won't know the values. The only place I know the moment is what? At A, at B, and at C. What are the values at A? What is the value at A? 0. At B? 0. At C, we solve for it. That's all I've got. Terrible problem. Why did I ever give you this? Terrible. You're welcome.